So chapter 11, controlling microorganisms. And as an introduction, what do we mean, or what are we going to do? Why are we using the antimicrobial control, and what is it? Anti means against, microbial, against microbes. So we are going to work against microbes in different ways. And when I say microbes, I mean any microbes. Whether it is harmful, this is our goal, but this is not what we're going to do. We're not going to differentiate. What we need to do is undesirable. Undesirable. Anything that's not supposed to be there. Clear? Anything that's not supposed to be there. Harmful? Yes, this is the best. But we are not going to focus on this. Anything that's not supposed to be there, which we call it undesirable. So there are different techniques and different ways that we will discuss. How to do that? There are different ways. There is a physical method, there is a chemical method, and other ways. Physical method is mainly heat. It's not only heat, but this is number one, heat. And heat can be dry or wet. So you can be just using heat to a certain point, dry, that's it. But we can use also wet, which is we're using steam on it. We call it the moist heat. You're adding water. These are the two types using the heat. Are you using the heat alone or with water? Heat alone, we call it the dry. If you add water, steam, that will be the moist way. We will discuss the details. So the other physical method, so physical method number one is heat, okay? Dry or wet. Physical method number two, radiation. Examples of radiations, gamma rays, X-rays, and even ultraviolet rays. We always say ultraviolet rays, this is something natural, it's in the sun. Yes, but they can have it in a higher concentration or a higher wavelength to kill the bacteria. So it does have some effect, like even the ultraviolet rays, like if you stay in the sun for some time, if you leave something in the sun for some time, the ultraviolet rays are going to clean it a little bit, not that much. But if you can change the wavelength of the ultraviolet, so you produce it, I'm not talking about the sun ultraviolet now, right? I'm talking about the ultraviolet that can be used with a different wavelength. That can be bactericidal. And if that's the case, what is it going to do? It's going to damage nucleic acid. And this is important to remember. So let me say it from the beginning. The way we kill organisms is extremely important. How do you kill it? How do you kill it? This is always something that you have to know. So here is one of them. If you are talking about ultraviolet rays, can it kill the organisms? Can it kill the bacteria at certain wavelength? Is that clear? At certain wavelength. Yes, we call it the bactericidal wavelength. It's a wavelength that's designed to kill the bacteria. And the suffix side or sidal means to kill, like suicide, homicide, right? Bactericide. So side is a suffix that means to kill. Bactericidal, you can kill the bacteria. Just the regular ultraviolet rays? No, there is a wavelength that's specifically to kill the bacteria. And how exactly does it kill the bacteria? By damaging nucleic acids. So this is for the physical agents, or the physical way. The chemical way is we're using molecules, organic or inorganic, it's molecules anyway. And these molecules are going to destroy the microorganisms. Whether they are going to kill or inhibit, and this is two different goals, we can use this or that. Whether we're talking about inanimate object or human body, in both cases it can be used, and we have different things that we will discuss in details. Disinfectant versus antiseptic, sanitizer, degermer, All these are examples of the chemical methods. But as a start, you need to remember that we're using molecules, whether it's organic or inorganic, that's number one. Number two, it can kill or inhibit. Are we clear? Kill means, what's the suffix? Cidal. If you're going to inhibit or slow down the growth, we call it static. So this is the second suffix, and you will see it. It will be repeated, but just understand from now. So you say something cidal or something static. Bactericidal, bacteristatic. Fungicidal, fungistatic. You get the idea? So if you say static, you're not killing. You're inhibiting the growth. Okay? Are you going to use the chemicals on your human body, like your hand, your foot? Some of them can be used, like soap, for example. This is a chemical, isn't it? It can be used. You can use, sometimes you use alcohol, right? Sometimes we can use iodine. And so Dettol. Don't we use Dettol? Yes, it can be used. And others can be used on inanimate only, like the oven cleaner, for example. Of course, you cannot put that on your hand, right? But it can be used to clean and kill organisms on the inanimate. The categories for the chemical, bactericidal or antimicrobial in general, it can be in different forms, and we have examples of those. But generally speaking, it can be liquid, it can be solid, it can be gases. So something like chlorine. Are we familiar with the chlorine? Where do we use it? For what? For the water. Yes, for the water. We can use it for the water. Iodine can be used on the hand. We can clean if we're going to do surgery or something like that. Alcohol can be used. Phenol, peroxide, aldehyde, gases, detergent. So all of these are different categories and different forms, liquid, gases, and solids, and we will have details to talk about. Whether we're talking about physical agents or chemical agents, which is the physical agent is based on energy. The physical agent is based on energy. We're talking about heat. We're talking about radiation, right? In both cases, how are you going to kill? Energy. Okay? Energy. Heat, you're using energy. Radiation, you're using energy. But for the chemicals, we're not using energy. We're using the molecule. And it's going to, whether we're talking about energy-based or molecule-based, in both cases, you are going to stop, inhibit, or kill the bacteria. Inhibit or kill. When I say inhibit, it's static. When I say kill, it's cidal, right? Whether you're doing this or that, when we say static, what do you mean by static? Inhibit the growth and reproduction. Is that clear? Inhibit the growth or reproduction. Did you kill? You didn't kill it. It's just inhibiting the growth. It doesn't grow and it does not reproduce. So it's extremely important to prevent the exposure to any microbe, generally speaking. And this started early, hundreds, maybe thousands of years ago. They know, even though they didn't know the details, but they did something like burning wood. They know that when we burn wood, that's going to help us to get rid of the microbes. That's it. Right? Or the bad things at that time. They don't know why, but we know that it's releasing formaldehyde. And formaldehyde is antimicrobial. They didn't know, but they used it. They also used herbs, perfumes, vinegar. These are all things that have antimicrobial activities. Even though they didn't know the details, but they used it, and they know what is it doing in generally speaking. In all cases, when we say microbes, of course, we're not only talking about bacteria. And when we say antimicrobial, anti against, We're talking about physical, chemical, or mechanical way. In all of this, we call it decontamination. Decontamination. So what's the decontamination? What's D? DE. Against, without, right? So decontamination is to remove the contamination. What do we need to know about decontamination? Two things. You can do decontamination using physical, chemical, mechanical, one of those. And what are you removing? Any contaminant. Any contaminant. What do we mean by any contaminant? Anything that's not supposed to be there. And you're doing that to prevent infection or spoilage. Infection, like for humans, for living organisms, but spoilage is for like food or stuff. So what are you going to kill when you say decontamination or get rid of? Bacteria. Bacteria is number one. When you say bacteria, I mean two things. Bacteria, the vegetative bacteria, which is the bacteria, the active bacteria is one thing, or the endospores. Which one is harder to kill? Endospores are a lot harder. Vegetative form, this is the easy one. The bacteria is moving, you can get rid of it somehow. Inhibit its movement, penetrate the cell membrane, you can do something about it, which is very easy. So what are the two forms of bacteria that you need to get rid of? Or you might need to get rid of? The vegetative and endospores. For the fungus, same thing. Fungus, same thing. We have vegetative form of fungus, which is easy. Endospores are hard. But let me say this, not as hard as the bacterial endospores. Even though it's an endospore for the fungus, but it's not as hard. The hardest of all is the bacterial endospores. Is that clear? Like extremely hard to get rid of it. Your only way, or the most effective way, is the autoclave. Okay? So this is the hardest of all. So when we say fungus, I mean vegetative form or spores. Vegetative form can be yeast or hyphae. Protozoa, same thing, but we don't have spores here. We have cysts. So it can be trophozoite or cyst. What's a trophozoite? The vegetative form. Cyst is like the egg, similar to the spores kind of. You need to get rid of the worms, viruses, and prions. Prions is not a living organism. Do you remember the prions? It's not a virus. What is it? Prions, PR starts with PR. Yes. Infectious proteins. It's not even an organism. Less than the virus. Not even a virus. At least the virus have genetic material, doesn't it? The virus can have DNA, RNA. That doesn't have anything, just infectious proteins. So in all cases, we need to get rid of one of these different forms, and we call that decontamination. Did we get the decontamination? Decontamination is a general term. Any method to get rid of it, and you get rid of anything. This is generally speaking, and then we will discuss the details later on. This is very important to know. The hardest, the highest resistance of all is the bacterial endospores, followed by the prions. Okay? Something like Clostridium tetani. Do we know the tetanus? We can take vaccine against tetanus. Yeah, tetanus is usually, the way we get it is in the soil or something. This is not the normal atmosphere. This is not the normal host for these tetanus bacteria. So they change to become endospores temporarily in the soil until we get it somehow. Like the most common way is that you go like in the soil and you have a wound or something. So you get these endospores and they change to become the vegetative form. But here is a question: what is the hardest to get rid of? bacterial endospores. You say it all together, not just endospores, because there are other endospores. Okay? Bacterial endospores, specifically. And prions. Moderate protozoan cysts, the naked viruses, staphylococcus. What's the staphylococcus? It's a bacteria. But why did we put it alone like this? Like here is bacterial endospore, and here you will see the vegetative. We put the staphylococcus alone, not highest, not least. It's moderate because even though it's a vegetative form of bacteria, but it is more resistant than any other vegetative form. And that's why if you have staph infection, most of the time they give you a combination of treatment. Okay? The least resistant are the vegetative bacteria, fungus, and protozoa. You have to remember this. So when I say the least resistant, what comes to your mind is vegetative form. Bacteria or fungus. Is that clear? What's the easiest to get rid of? What comes to your mind? Vegetative. Vegetative what? Bacteria and fungus. This is the easiest. What's the highest? The most resistant? Bacterial endospores. Okay. So here are different agents. You don't have to know all these details. All what I want you to know here is, look at the method. We can use heat. We can use radiation, like X-ray. We can use sterilizing gas, like ethylene oxide. We can use sporicidal liquid, like glutaraldehyde, for example. So these are examples. The only detail that I want you to know is this. These numbers. Okay? If you are talking about heat, when you heat something, like we boil milk, we boil stuff in our house, right? We boil stuff. When you go to 80, even 90 or 100, or what you're killing is a vegetative form only. Okay, even if you go to 100, 110, the point that you start to kill the endospores is 120 or above. Is that clear? So you have to remember this number, the magic number. What's the magic number? Above 120. You have to go above 120. So how about 110? No, not enough. 110 or 100, that will get rid of the vegetative form. It will not kill the endospores. What's your magic number to kill the endospores? 120 or above. Okay? Other than that, here's what I want you to know. The vegetative form takes less time, smaller dose. That's it. For any one of those. Than the endospores, right? Irrespective of the numbers, you can take a look at it, but just understand that the vegetative form is easier. What I mean by easier, less dose, less time. How about the endospore? More dose, more time. That's it. The most effective way for sterilization. What's a sterilization? Destruction or removal of all. This is your clue here. All viable organisms, including resistant endospores. Like you make it zero, literally zero, nothing at all. Even the resistant endospores, yes, everything. And this is the autoclave. So did you get what sterilization? We will go to the other things, disinfection and sanitization and all that stuff, but you need to remember this word, sterilization. Sterilization means all, including resistant endospores. Is that clear? Sterilization means all, everything. So when you're done with the sterilization, zero, nothing at all, even the resistant endospores. And this is your autoclave. Anything else is not that effective. This is the most effective. So did you understand sterilization? Because this is number one. These agents microbial agents, microbicidal, germicidal. What cidal means, or what sides means? Killing. Cidal means killing. Static means inhibit growth or stop reproduction. Right? Did you kill? No. Static, you didn't kill. Okay? So if you talk about microbicidal or germicidal, these are agents that kills. And you should be specific here. When you say cidal, are you talking about bactericidal, fungicidal, virucidal, sporicidal? So can you tell me what does it mean? What's bactericide mean? Kills bacteria. Fungicidal. Kill fungus only. It doesn't kill anything else. Kill fungus. Kill virus. Kill the spores, right? So these are different things. Now the terms that are extremely important to know for this chapter. Disinfection is number one. And then you will go to antisepsis and other things. This is extremely important to know. Okay? Disinfection. What disinfection? Here, generally speaking, disinfection is you're using an agent, physical or chemical, whatever it is, to destroy vegetative pathogens, not endospores, on inanimate objects. So let me give you this. Look at this. When you go to this is very important, okay? So you always talk about two things, right? Am I killing the vegetative form or the endospore? This is number one. Am I doing that on a human body or inanimate? Is it animate, inanimate? Two things to focus on, right? What I am killing on what? What I am killing on what? Okay? So disinfection. What I am killing? The vegetative form only, not the endospores. And this will be inanimate. You call that disinfection. When you do the exact same thing, but on living tissues, you're talking about something else. Is that clear? So this is number one. Number two, antisepsis. You're using a chemical agent, for example, antiseptic, on body surface to kill vegetative pathogens. Is that clear? So this is disinfection versus antisepsis. Disinfection, what are you killing? Vegetative or spores? The vegetative only. You're not killing the spores. On what? On object, inanimate. How about the antisepsis? On what? Body surface, and you're killing vegetative form, not endospores. So what do you call it when they kill the endospores? It's none of those. Sterilization. I didn't talk about sterilization yet. I gave you an idea, but here it is. This is a complete removal of all viable microorganisms, including endospores. And this is usually done on inanimate objects. The most effective way to do sterilization is? What's the most effective way? Autoclave. Autoclave. Obviously, this is inanimate. Can you put like your hand in the autoclave? Of course not, right? You can't put your hand in the autoclave. It's going to like steam and heat. It has to be inanimate. So what can we put in the autoclave? We can put most likely the surgical instruments, for example, because you're using surgical instruments. You cannot have anything, not even endospores, right? So this is for sterilization. So here is disinfection, something like this. Is a disinfection kill the endospores? No. Disinfection, is it on living surface or inanimate? Disinfection, inanimate. Antisepsis, animate. To remember it, the only way, the only definition that gets rid of the endospores is sterilization. When I ask you, automatically don't say endospores until we say sterilization. Okay? Something like this, for example. Why are we using Listerine? Soap or any cleaning on our hands. This is called antisepsis, and it's going to kill the vegetative form only. Okay? And because of that, the antisepsis is generally speaking, is less toxic than the disinfectant, right? Why? Because you put this in your mouth, right? Yes, you wanted to kill the bacteria, you wanted to get rid of as much as possible the vegetative form, but if you look at disinfection, you can go more than that, right? You can be more strong because there's nothing to worry about, right? I'm cleaning the countertop, for example. Why I have to be careful, right? I can use stronger and more toxic agents, right? Make sense? So generally speaking, which one is more toxic? Antisepsis, because we have to be mild, right? You're using your body surface, you have to be mild. You can't use very toxic. But if it's inanimate disinfection, you can use anything, right? So it's more toxic. The next terms are sanitization versus degermination. Sanitization is not much different than disinfection, but I'm giving you certain words that you need to remember that will make a difference. You're also getting rid of the debris. Okay? Debris. So what's the difference between sanitization and disinfection? Isn't it almost the same? Both of them are the vegetative form and both of them are inanimate. Both of them, right? What's the difference then? Sanitization is also removing any debris, not just microorganisms. Is that clear? Degermination, D means removing, without. Germination, it means removing the germs. You remove as much as possible of the load, microbial load, from living tissues by mechanical means. Like this. Look at this picture, like you go wash your hands. This is a physical method, right? When you rub using a sponge or something, using a physical method. Are you really killing everything? No, you're just decreasing the load, right? As much as possible. This is degermination. If you look at this, this is a general map for everything that we're using. So you can use physical, chemical, and mechanical agents, right? Physical, chemical, mechanical. When you say physical, I mean heat and radiation, right? Heat and radiation. Heat, it can be dry, it can be moist. If it is dry, it can be incineration or something like dry oven. Incineration will do sterilization, and dry oven will do sterilization. So in both cases, you're doing sterilization. For moist, not necessarily. If you're moist under pressure, this will cause sterilization, and this is like the autoclave. If you're not doing pressure, if you're not using pressure, like using boiling water, hot water, pasteurization, and we'll talk about those. But this is disinfection. What do you mean? Disinfection. Did we kill the endospores? No, we didn't kill the endospores. Is that clear? So if you're using the moist heat, under pressure or not, under pressure, sterilization. Okay, heat under pressure, and it has to be above 120, right? Heat under pressure, sterilization. Not under pressure, like boiling water, hot water, pasteurization. In all cases, you're just doing disinfection. So unfortunately, you didn't get rid of the endospores. The other physical agent is radiation, and radiation is two types. We have two types of radiation: ionizing and non-ionizing radiation. Non-ionizing radiation is ultraviolet, and this is only for disinfection. Okay? And what does it work on? How does it disinfect? Ultraviolet. How does it kill the bacteria? It will work on what? On the bacteria. Start with N. N. Not M. N. Nucleic acid. Nucleic acid. Okay? You have to remember the way they kill the bacteria. Okay? This is important. Okay? So what kind of radiation do we have? Non-ionizing, ionizing. Non-ionizing is ultraviolet. Of course, ionizing, this is very strong, right? You're not supposed to be exposed to any ionizing. This is too much. But non-ionizing, like ultraviolet, if we go out in the sun, right? We're exposed to sun, it's not ionizing. So it's not that harmful. but they can do disinfection. And if we change the wavelength, it can kill the bacteria by disrupting the nucleic acid. Ionizing, this is a very strong agent, something like X-ray, cathode, gamma rays, and this will cause sterilization. If you ever did X-ray before, if you notice, they have to put something on your chest, right, to cover, because this is ionizing radiation. It causes sterilization, but it can kill your own cells, right? So that's why they always cover, but it needs to be repeated. But anyway, we need to remember that this is ionizing versus non-ionizing. Ionizing sterilization, non-ionizing disinfection. Chemical agents can be of different forms. Gases, for example, it can do, depending on which gas are we using, it can be sterilization or disinfection. What's the difference between the sterilization and disinfection? One word. Endospores. Endospores. Difference between sterilization and disinfection, most important. Endospores. Did you kill endospores or not? Okay? Liquids, you can use liquid on animate or inanimate. If it's inanimate, you call antisepsis. If it is inanimate, it can be disinfection or sterilization. Mechanical method, you can use filters, for example, like air filters and liquid filters. The air filters will just do disinfection. Liquid, like sterilization. Like the good example for that is, did you ever look at your air conditioning unit in the basement? Did you ever change or see how we change the filters? Did you see these filters? Yeah, these filters are for air to disinfect. But you need to know that while doing that, it doesn't get rid of the endospores, right? While the liquid method, which is used more for clinical use, medical use, this is for sterilization. Okay? This is the general map of all these agents. So here is a table that's I put it together to give you all the comparison, and I put color code to remind you which one is animate and which one is inanimate. Okay? So generally speaking, decontamination is using anything to get rid of anything. Clear? This is so not specific yet. Sepsis means the growth of the microorganisms in the tissues. We call that sepsis. Like if I have a wound here and you see the wound started to become yellow colored, start to ooze, right? We call that sepsis. Okay? Asepsis means, what's A at the beginning? No. Yes. Asepsis means preventing sepsis. Preventing sepsis. Example of that is before they do surgery, they use some chemical agents like iodine. They always use it before surgery. They sterilize the needles before using it, right? Or the needle is sterilized already. And if this is another form of needles that we need to use for medical use, they have to sterilize it first. If you're talking about the needle of the syringe that we like get antibiotics or something, this is already sterilized. But if you're talking about something in a lab, they sterilize it. Okay, so this is asepsis. And the asepsis is more of prevention, something to use before. But all of the five is what we talked about. Antisepsis, degermination, those two on animate surface. Animate. The others, disinfection, sanitization, sterilization, these are all inanimate. So I put a color code to remind you, okay? Anti-dish, if that's going to help you. Anti-dish on human surface, anti-dish. Anything else? Inanimate. Anti-dish, animate. Okay, can you answer this question? C? Yes. Anti-dish. on human surface. So when you talk about microbial death, when you talk about killing the microbes, you can kill them actually, or you can stop their reproductive capabilities. Okay? So if we are using whatever the agent is, what are the factors that will determine the microbial death? And this is important to remember. Okay? You have to remember this. What are the factors? Like, I'm trying to kill these microbes. What determines if I will be able to do it or not? Number one, the number of microbes. Of course, it's different if you have a little bit versus if you have a big amount, right? So the number of microbes is one. The nature of the microbes. What kind of microbes do you have? Do I have like a vegetative form? Do I have endospores? Is it bacteria? Is it virus? And so on. The other thing is temperature and pH. This is going to determine, because what you're trying to do here is changing the normal environment of the microbes, right? Changing the normal environment. So each microbe will like or love a specific environment. Like, did you ever ask yourself why when you have infection or inflammation, why you get fever? Think about it. Or if you have like inflammation here in my hand, do you notice that it's getting warmer? If you ask yourself, why is it getting warmer? There are different reasons for that. It's not to bother us. It's, number one, to increase the activities and increase the metabolism, to get more energy. But the other thing is, and this is what the point I'm trying to make here is, this fever or this warmer is not a good environment for the microbes. They don't like it. The microbes that invade us, they love our normal temperature. Is that clear? They love our normal temperature. If it is 37, they are happy. 37 or 98.6, they are very happy. This is their normal environment, normal temperature. When you increase it or decrease it, that's bad. Okay? pH, they also like our pH. What's our pH? 7.35, 7.45. They like that. You change it, it's bad for them. Okay? The other thing is the antimicrobial agent that you're using. What's the concentration? What's the dose? The bigger dose, the more effective, right? The mode of action. How does it work? Does it work on the membrane? Does it work on the proteins? And so on. Do you have anything else like solvents, inhibitors? Do you have anything else that's going to help? So you have to remember this. Okay? So when you choose something and you're concerned about the microbes, you have to ask yourself some questions. I'm using this instrument. Does it need sterilization or not? Can I reuse it or not? Example of that, the syringe, right? If you're using syringe to inject something, is it reusable? Can you like inject and keep it for next time? Of course not. It's not reusable. Why not? Can you like put it in the autoclave? No, it's plastic. You can't. Right? Can I reuse my surgical instrument? Yes, you can put it in the autoclave. Right? So it does require sterilization. Does it require or not? I'm using the syringe. It's already sterilized. I don't need to. Right? So you ask yourself, if I need to sterilize, can it take the heat and pressure or radiation? I'm going to use heat or radiation or pressure or chemicals. Does it take it or not? What am I going to use on my hand versus what I'm going to use on countertop or any other method? Is this method suitable or not? Does the agent, can the agent penetrate? Like, can it penetrate the membrane? if we're talking about this specific microbe versus others. Cost-benefit relationship is another thing. They will cost me this, and this is the benefit. I have to make sure that the cost-benefit is fine. Okay, did we do this before? I think we did. Okay. So what's the target? Which is the way, I'm being specific here, the way to kill the bacteria or the microbes. How exactly do you kill it? Details. You can work on the cell wall and you make it fragile so that the cells are going to die. Lyse, breakdown. Antimicrobial drugs, which is the next chapter, we're not talking about this right now, but detergents and alcohol do that. I want you to remember this. If I ask you how the alcohol work, how the detergent work, you have to tell me cell wall. Is that clear? You have to be specific here. Alcohol and detergent, they work on the cell wall. Cell membrane. Phenol and phenolic derivatives, they work on the membrane. Is there a difference between the wall and the membrane? Yes. The membrane is every cell. The wall is on some cells, bacteria specifically, right? So something like soap, for example, how does it work? Like when you clean the dishes with soap, what exactly, or your hands, what exactly is happening? The soap is a surfactant, okay? The soap is a surfactant. The surfactant is going to mobilize the fat so that when you remove the fat from the wall, remember the cell membrane, the phospholipid bilayer, remember that in physiology? There is lipid in the wall, right? So if you move this lipid around, the wall will be disrupted and it's going to break down. So how the phenol and phenolic derivatives work? Membrane damage. Membrane damage. When you say membrane damage, I'm talking about the lipids. Like soap, for example, how does it work? Cell membrane. Are we following? How does the soap work? How does the phenol and phenolic derivatives work? On which part of the microbe? Cell membrane. Which part of the cell membrane? Lipids. Lipids. Okay? Some others will work on nucleic acids. Did I talk about ultraviolet before? Ultraviolet radiation, if it is in a bactericidal wavelength, how does it work? Nucleic acid, right? Nucleic acid. So what work on a nucleic acid? Ultraviolet radiation, X-ray, ethylene dioxide, formaldehyde. Do I need to remember this? Of course, yes. You have to remember this. How exactly does it work? I think I'm being very specific here, right? How does it work? Phenol, phenolic derivatives, and so they work on the membrane. Alcohol work on the wall. This is one. And nucleic acids, radiation, ultraviolet radiation, X-ray, ethylene dioxide, and formaldehyde. You have to remember these agents. I can ask you about each one of those. How does the formaldehyde work? How does the ethylene dioxide work? How does the X-ray work? Nucleic acid. We work on the nucleic acid. Which level? Any level. This is not our issue. They can work on the transcription, translation. They can break down the peptide bonds. You remember the DNA? We talked about it before. They work on any level. But in all cases, our word is nucleic acid. Nucleic acid. How about protein function? Like denaturing proteins. Which ones work on those? Alcohol, phenol, phenolic derivatives, acids, and heat. Did we say phenol and phenolic derivatives before? On what? On the membrane. So does it work on the membrane or the protein? Both of them. Both of them. Okay? Did we mention alcohol before? It works on the wall, but it works on protein as well. Okay? So when I say alcohol, we say wall and protein, denatures. When I say phenol-phenolic derivatives, you say membrane and protein. Denature means change the nature. Acid and heat do the same thing. Meaning, if you get a raw egg, right? And the egg white is semi-solid or liquid form, isn't it? It's liquid, kind of. And it is transparent to a good extent, right? When you expose it to heat, or acid, or alcohol, or phenol, you know what's going to happen? The nature will be lost. It's not liquid, it's not transparent. What does it look like when you expose it to any one of those? What's the color? Does it become white? What happened when you boil the egg? Is it transparent and liquid anymore? No. It's solid and white, isn't it? Did it change the nature? Yes. We call that denaturation. D, without removing nature, is the nature, the natural characteristics of, like in this case, it's the egg white. Okay? So here is the mode of action. This is the native state. You can use something of the, one of the things that you can use is the heavy metals can be used as well. They can block the active sites. So they are going to kill it this way, block the active site. Heavy metals block the active sites. So the active site is not available anymore, so the enzymes cannot work, so you are deactivating. This is when it gets completely denatured, like when you use the heat or something, it's folding like this, or the heat, or pH, or alcohol, or phenol. What is it going to do? It will change the nature like this. Can you tell me the answer for this? A? Yes. Did you get it? If I ask you alcohol, you should say wall and protein. Denaturation. So let's be more specific now. Physical methods can be heat, cold, drying, called desiccation, radiation, filtration. Filtration is a mechanical method. Physical, mechanical. So these are the physical methods. Heat can be moist or dry. We talked about this before. So moist versus dry heat. What's the difference between those two? Moist, you're adding water, isn't it? You're adding water. So steam and heat. Dry heat is just heat. Okay? Just heat. And you're not adding anything to that. So what's the difference between those two? Here is the difference. Moist heat is more effective than dry heat. More effective means it's stronger and faster. Which one is stronger and faster? Moist heat, stronger and faster. If I'm using moist heat, I don't have to increase the temperature that much, and I don't have to wait that much. If you're using dry heat, you have to use higher temperature and you have to wait more. Okay? If the heat is moisted, sterilization at 100 degrees centigrade is going to kill everything except what's not killed at 100? Endospores. Endospores. So what do you kill? You kill the vegetative bacteria, the vegetative fungus, even the fungal spores and viruses. Is that clear? So when you get to 200 boiling, you get rid of almost. Like you ask yourself, why I'm boiling stuff when I'm cooking or something? Why I have to boil? You're getting rid of everything minus endospores. This is the only thing that you cannot get rid of. But did you get rid of everything else? Yes. Dry heat, on the other hand, you have to use higher temperature, and it will take more time. And how does the heat work? 13. I showed you in a previous slide. This is very important, right? Is it wall, membrane, nucleic acid, protein? You remember those two slides? Very important. Each one of those work differently. Okay? Dry heat, the common use for dry heat is in the laboratory to sterilize inoculating lobe. What is inoculating lobe? Like, if you ask yourself, why don't I just use the moist heats? Because it is stronger and it takes less time, right? Dry heat, sometimes you can use it. Like inoculating lobe. Like if I'm taking sample from your body fluids and I put it on a Perti dish, for example. Before doing that, did you see that in the lab before? They put it on a flame for some time. This is a dry heat, right? So they sterilize it and then they take like a swab, they take the sample and they put it like on a Perti dish or tube or something like that. But in all cases, you have, if you wanted to sterilize, what's your magic number? Above 120. So this is a comparison, and what I want you to know from this comparison is not really the numbers. The one number that you have to remember is the magic number, above 120. Is that clear? But here is the moist heat. If you increase the temperature, you need less time. That's it. So 121, 125, 134, all of them would work. All of them were sterilized. It's just when you increase the temperature, you need less time. That's it. Okay? For both of them. Is that clear? In all cases, it has to be above the magic number. Endospores are the most resistant. Vegetative states of bacteria and fungus are the least resistant. Right? So if you wanted to kill all microbes at a specific temperature, the shortest length of time is called the thermal death time. Thermal death time. Thermal means heat or temperature. So thermal death time is the death time, the time that you need for death at certain temperature. So just read it. Death, thermal death time. The time that's needed for death under specific temperature. Okay? Thermal death point is the lowest temperature that can kill all microbes. In all cases, you're talking about all, right? So when you say thermal death time or thermal death point, you have to say everything. How does it take? Whether we're talking about the time or the temperature, in order to wipe off or to kill all microbes. This is the use of heat. They use different things in the lab for the thermal death. So the autoclave, what is it using? Steam under pressure. It's steam, we mean moist heat. So what's the autoclave using? Moist heat or dry heat? Moist heat. Under pressure or no pressure? Under pressure. So moist heat under pressure. When I say autoclave, what comes to your mind? Moist heat under pressure and sterilization. Okay? What if if I wanted to use sterilization, but not the same way, but not under pressure? Yeah, there is another. There are other instruments that can do that without using the pressure. Tendalization. This is what we call it. So are you sterilizing with moist heat? Yes, sterilization or you can use the autoclave and you can use the tendalization. Autoclave is under pressure. Tendalization is not under pressure. How about boiling water and pasteurization? Does that sterilize? It does not sterilize. Disinfect. Pasteurization, disinfect. Okay, sterilization, heat above 120. Moist, under pressure or not under pressure, this is something else. If you're putting something in autoclave, this is autoclave, by the way. This is how it looks like from inside. So if you're looking at the autoclave, when I say autoclave, can you tell me the magic words? Autoclave, what you should remember. Moist. Moist heat under pressure. And what's the goal? Sterilization. Moist heat under pressure, sterilization. Okay? What exactly can be used with the autoclave? Anything that will not be destroyed, right? You cannot put like something plastic inside. You can't do that. So it has to be something that's heat and moist resistant, not sensitive to moist or heat. Otherwise, you're destroying it, right? How does it work? Denaturating proteins of the membrane and DNA. You have to remember this. I mentioned from the beginning the technique, the way, the exactly they kill is important. Details, right? Protein, nucleic acid, wall, membrane. How does the autoclave kill? Denaturing proteins of what? Membrane, and it also works on the DNA. Are we clear? Details are needed here. Before using the autoclave, you can actually do some washing and mechanical removing of the bacteria, which we call it degermination. That will speed up the sterilization process. So here's what they do. Instead of taking that dirty instrument, they don't do that. Okay? They don't take the dirty instrument and throw it in the autoclave. They don't. They take it first and wash it and clean it a little bit, so you're decreasing the microbial load, and then they put it in an autoclave. Tendalization, no much details. All what you need to know here is it's still moist heat, but not under pressure. Are you sterilizing or not? Yes. Sterilizing, moist heat, but not under pressure. Simply, they go in cycles. Okay, they use the steam, they leave it for some time, for like a day, and then they do it again, and then leave it for some time and do it again, and so on. And this is a technique that's used for canned foods. Sometimes it's used in a laboratory, but most likely it's a canned food. So, of course, in canned food factories, they do not use the autoclave. Okay, so this is the practical use. Are we following? So what's the practical use for autoclave? It's more for medical use in the lab. Clear? How about tendalization, which also sterilize? This is more for canned foods. Boiling water, does it sterilize? No, does not sterilize. What sterilize? What's the magic word? Killing what? Endospores. If you boil something, are you killing the endospores? No, you're not. But if you want to kill everything else, not the endospores, it's 100 degree for 30 minutes. Okay? Don't tell me like I left it there until it started to boil and then I stopped. That's not enough. You have to leave it for 30 minutes. After you put it on 100 or more, and for 30 minutes you still didn't kill the endospores. Okay? Pasteurization. I think we know the pasteurization. When you disinfect liquids like milk, apple juice, any kind of juice, wine. When you hear pasteurization, we're talking about something that we drink, whatever it is. Pasteurization is you disinfect something that we drink, okay, whatever it is. Does that sterilize? It's not a sterilization. It's not sterilization. Sterilization is autoclave and thermalization. So you're going to kill most of it, but it's not sterilization. Just for your information, the first time that we use the pasteurization, unlike what we think it's the milk, right? The first time it's milk, it's actually wine. This is the first time that they use the pasteurization. Wine, and then they used it for milk and other things. If you're using the dry heat, if I'm using dry heat, do I need higher temperature or less temperature? Lower temperature compared to moist heat. I'm talking about the dry heat. Do I use it for higher temperature or lower temperature? Higher temperature, because it's less effective, isn't it? It's less effective. So if you're using dry heat and moist heat, which one is more effective? Moist heat. Which one needs lower temperature? Moist. Which one needs less time? Less time. Moist. Okay? Simply, moist is stronger, isn't it? Moist is stronger. So I need less temperature, less time. Okay? When you say terms like incineration versus the oven, what's the difference? Incineration is you're using flame or a coil, that's electrical heating, or even infrared incinerators. So we call that incineration. So incineration, you are using flame or a coil, electric heating coil, and so on. And this can cause heat sterilization. If you're using the oven, can you sterilize using the oven? Yes, but you have to go to 150 to 180. This is how high you need to go in order to sterilize. And how does it work? You work on proteins, denaturation. Protein denaturation. Okay? Coagulation means denaturation. It's the same thing, coagulation. So this is the heat sterilization. Okay? So does incineration can incineration and hot air ovens sterilize? Yes, they can, but under higher pressure. So do you remember 4 now? It's not 2. Autoclave is 1. The thermalization is 2. Incineration and hot air oven or dry air oven, all of these can do it. But you have to go to a certain degree in order to do it. Unlike the autoclave, you just go to 120, above 120. But if you wanted to sterilize using and they use it, by the way, in the lab. They don't have, not all the labs have the autoclave. Sometimes they just have this hot air ovens and they can use it, but they have to put it up to 150 to 180. So you need to do more. How about cold and freezing? This is not going to kill. This is static. What static means? Growth and reproduction. Slow down or stop the growth and reproduction. You don't kill, right? So if you put something in the fridge, do you think the bacteria there is going to die? It is not going to die. It's not going to grow. Okay? What do you think will happen if you go to your fridge and you put the thermostat up, like it's 1 or 2 or 5, and then you put it on 10? Yes, it will be spoiled, right? Why? Because it's not doing the static effect anymore. So cold or freezing is microstatic, microbiostatic. It's going to slow down. It's going to stop. That's sterilized. Can you put it like in a fridge? Now it is sterile? No, you cannot. Okay? Between 0 and 15, this is the refrigerator. Everybody's doing it different. If you go to 0 or less, this is freezing, right? Usually our fridge is 2 parts, isn't it? Like this is the freezer, this is the fridge. Freezer is less than the 0. The fridge is between 0 and 15. If you go above 15, it's not useful anymore. Whatever you put there, it's going to be spoiled, right? Okay. So this is more for preservation, but is that static or sidle? Fridge and freezer, is that static or sidle? Static. Desiccation. Desiccation is drying. You dry something, and what drying means? You remove the water. When you dry, you're removing the water. And why are you removing the water? Again, you're disrupting the good medium for the microbes. What does the microbes need to grow? They need a good temperature. They need a good pH. They need the water, right? This is what they need. So when you dry something, you are temporarily inhibiting them. But it's not a sterilization, and they do not die. Once they get the water again, they are going to regain their ability to grow and replicate and so on. Lyophilization is freeze drying. So what's desiccation? Drying. Desiccation, drying. Lyophilization, freeze drying. Freeze drying. Are these sterilization techniques? No. Which one of those? Yes. Incineration. Which one of those? B? Yes. Okay. Next physical agent is radiation. Does the radiation use molecules or energy? Energy. What use molecules? Chemical agents. Chemical agents. Physical agents use energy. Chemical agents use molecules. Okay? It can be ionizing or non-ionizing, and we talked about this before. What's the one that's non-ionizing? Ultraviolet. Everything else is ionizing, which is more harmful. Okay, so this is just giving you an idea about from red to violet. If you go above that, you are ultraviolet. If you go under the red, this is infrared. So obviously from red to violet, this is our normal wavelength that we can see, right? And this doesn't do anything from red and violet and anything in between. But if you go under the red, if you go above the violet, this is the radiation that can be used. Okay? How does it work? Ionizing, it breaks DNA. Do I need to remember that? Of course, yes. It breaks DNA. It does sterilize. Non-ionizing, interfere with the replication. And does it sterilize? Non-ionizing? No, it does not. It just disinfects. Okay? Are we following what's... We have 5 that sterilize so far? 5? Are we following? 5 that can sterilize. This is the 5th one, ionizing radiation. Remember that slide that I showed you that's mapping everything? It contains all of this if you want to refer back to it. But if you put it together as we go, that will be something good to remember. Ask yourself, what are the 5 that I should remember for sterilization? Ionizing radiation is the 5th one. Other than that, we have the autoclave, we have thermalization, incineration, hot air oven if you go between 150 and 180, and so on. How does it work? Extremely important. Okay? Here is what happened when you use the ionizing radiation. Look at this. It goes to the DNA and it's going to break it down. Ionizing radiation. Does it sterilize? Ionizing radiation? Yes. This is the 5th one that does the sterilization. Non-ionizing? No, it does not. It does not. It just inhibits the replication. So that's not enough. When you inhibit the replication, that's not enough. You didn't break it down. So if you leave it alone, it's going to replicate again. This is the different uses they can use. They can irradiate foods, and this is how it looks like before and after. They do irradiation of the male just in case if there's a male coming that have something, microbes. In the hospitals, they use the ultraviolet robot. They can use certain gadgets for the ultraviolet. But when I say that, you need to remember something. I'm not talking about the natural ultraviolet that come in the sun. Is that clear? I'm not talking about the natural ultraviolet. This is an altered. They alter it. They change the wavelength of the ultraviolet radiation to be used as disinfectant. Filtration. Filtration simply a physical method to remove the microbes. From air or from liquid, we have different things. But it's a physical method. Okay? HEPA filters, did you change the filter in your, or did you see how it changed the filters? This is an example of these filters. HEPA filters remove the microbes from the air, and they count on the size of the microbes. You know how does it work? If you think about it, like why they always tell us you have to change your filters. They always tell us that, right? Every 2 months or 6 months or something, right? What exactly is happening? If you go to the air conditioner and look there, you see the filter. The air is coming from one side. It goes through the filter. The filter have very small pores, smaller than the microbes. It has to be smaller than the microbes. Okay? So when it goes inside from this side, anything will be filtered, it will stay, and when it passes through, the air is passing without the microbes. So it counts on the microbial what? Size. It's a physical isolation. It doesn't kill, it doesn't do anything. This is just a filtration. Did we get the filters? How do they work? Do they kill anything? They do not kill anything. They just depend on the size. Okay? And this usually does not include the endospores, here is the issue that we're having with the filters. If this is just for your own information, why they don't do filters that small enough to even block the endospores? Because this is not going to give you the air that you want. The air conditioner will stop working. Okay? It has to be extremely small to the extent of the air that go through it. It will not come out from the other side that much that you need, no matter what you do. So the air conditioner will be useless if you do that. And actually it can break down. Okay? And that's why there are recommendations. This is just for your information. They always recommend, they tell you the size, right? This is what you need to use. Up to a certain size. There are some sizes that can block the endospores, but it will break down the air conditioner. Okay? But the bottom line is the filters work on physical isolation, and it depends on the size of the microbes. Okay? Chemical agents, they remove anything that's not desirable, whatever we're talking about, disinfection, antiseptic. When you sterilize, you call it sterilant. When you do degermination, you call it degermer. When you do preservation, you call it preservative. Are we following? What are you using to sterilize? Sterilants. What do you use to disinfect? Disinfectants. What do you use to antisept? Antiseptics. What do you use to degerminate? Degermers. Is that clear? What are you using? In order to say this germicide is good quality or not, is it the desirable quality or not? Number one is rapid action in low concentration. I don't have to add all this amount to kill. This is not good. This is not desirable, right? What I need to use is something in low concentration. It does the action fast. Solubility in water. This is a good thing and should be stable. Should be broad spectrum and low toxic. And when you say toxicity, when we say low toxicity, what do we mean? Toxicity is the ability to kill the microbes without harming you. Low toxicity means it kills the microbes and it's not toxic to your body. Did you get the idea? When you say toxicity not to us, toxicity to the microbes. If it is toxic to us, of course we're not going to use it, right? Can you use like oven cleaner on your hand? Of course not. This is toxic. Low toxicity is like soap, detergent, stuff like that. If it penetrates, it's good, desirable. It should not be corrosive. Cannot use the oven cleaner or something. It should not be staining, otherwise we wouldn't use it. Should be affordable. So these are all desirable qualities. When you talk about germicides, you try to fulfill all of these characteristics. So the high level of germicides are the one that kills the endospore. Intermediate level, they will kill the fungal spores but not the bacterial endospores. And they can also kill the TB and the virus. The low level will only take care of the vegetative bacteria, fungus, and a little bit of viruses, like Clorox. We use it, right? Clean your hand. If you go to a grocery store or something, you usually have it, right? We say like wipe it before you use it or something. This is a low level. So all what you're getting rid of is some bacteria, like if you take one of these carts in grocery stores, right? Most of the time it's good to wipe it off, right? You wipe it with Clorox or something. What are you doing here? I'm just killing the vegetative bacteria, fungus, and a little bit of viruses. Like you don't know the person who used it before me. Maybe he has colds or something, which is a virus. You can get rid of it. Maybe some vegetative and fungus or bacteria, and this is good enough for those. But does this low level going to take care of the fungal spores? No, this needs the intermediate. Does it kill the bacterial endospores? No, it needs the high level. Are we following? High level kills bacterial endospores. Intermediate level, fungal. Low level, vegetative, and some viruses. Intermediate also kills some virus and TB. What determine the germicidal activities? The nature of the material treated, meaning, are you talking about your hand? Are you talking about your countertop? Are you talking about medical instrument? Right? So this is all different, because obviously you can do more with the instrument than what you can do with your countertop, right? Than what you can do with your hand. The degree of contamination, how much contaminants, which is the microbial load. Time of exposure. Are you going to leave it there for some time? How long was it exposed? The concentration. Are you using something that's highly concentrated or not? Okay, this is important to remember. These are some examples for chemical agents used in healthcare. I think we know of chlorine, right? Chlorine, we add it to water. This is sporicidal. What sporicidal means? It kills the spores. This is obviously good, but it's intermediate. It does not kill the bacteria in the spores. Is a chlorine toxic? Yes, it is toxic if you increase the amount, the concentration. You're not supposed to use it in high amounts. Okay? How about the iodine? It is sporicidal, slow sporicidal, and it is intermediate. Phenolics, it's slow to intermediate. Chlorix iodine, this is low to moderate. So obviously when we say low to moderate, do we know what we're talking about? Low to moderate to high. Low vegetative forms, bacteria and fungus. Intermediate, fungal endospores and viruses. High, how about the high? Bacterial endospores, yes. Other examples, alcohol, it's intermediate. Hydrogen peroxide, this is high, and it can sterilize. Did you use hydrogen peroxide before? You can get it from the pharmacy. Did you use it before? You put it like, give you these bubbles and stuff. Ammonium compounds. Soap, this is very low, but you're using it to get rid of the vegetative form at least. Mercury, it's bacteriostatic only, which is low. And you can see the toxicity levels also, like all of these are toxic to some extent. Hydrogen peroxide is toxic to the eye or if ingested. So the practical use for hydrogen peroxide is if you put it on your skin or something, right? That's okay. But you cannot take it, you cannot, your eye should not be exposed to any of those. Other examples, silver nitrite, dyes, ethylene oxide gas, sporicidal, and so on. The germicidal categories, it can be halogens, phenols, chlorhexidine, alcohol, hydrogen peroxide, aldehyde, gases, detergent, heavy metals, dyes, acids, and alkalis. Halogens, you need to remember that chlorine is a halogen. How does it work? The nature proteins. And it is unstable to sunlight. Can you remember this? Chlorine is one of the halogens. It's a germicidal. It's one of the halogens. Like bleach, for example. How does it work? The nature proteins. Okay? Do we need to remember this? Yes. Okay? And this will be your activities for today. This is what I want you to do. Whether you do it here, you do it home, that's fine. Okay? Just do a card, flashcards, and you put chlorine is a halogen, on the other side, the nature protein. Okay? Alcohol in one side, the other side is wall, the nature protein. Okay? You don't have to use actual flashcards. You can get paper and cut it into pieces. Okay? and you just show it to me. Okay, of course I'm doing that to help you study. Okay, it's not something that's not related. That's how important it is, and that's why I make it as an activity. Okay, so you go through the chapter, and you see something, and how does it work? You put the something on one side, how does it work on the other side? Can you do that? Okay, that will be your activity. So for the chlorine, it's halogen, it's denatured proteins, this is how did it work, and it's unstable to sunlight. So you're not, Clorox or chlorine, you're not supposed to leave it outside. The other halogen is iodine. So iodine is halogen. You need to remember that. It's also denatured protein. This is the most important that I'm talking about. Are we following? I'm not saying everything. It is what I want. Halogens, like chlorine. Chlorine, how does it work? Denatured proteins. What's the other halogen? Iodine. How does it work? Same way. Denatured protein. This is how they actually use it. Like if you're going to do surgery here, okay, like if you're going to insert a needle and take a sample or something, they have to like use the iodine around, and it's going to denature proteins. Denature proteins of what? Of the microbes and viruses. Unfortunately, it does not kill the endospores, but it's good enough to get rid of the vast majority. So iodine is a disinfectant. This is how they use it for in industry, like cantaloupes here, they disinfected with water that's treated with chlorine to get rid of the salmonella. Obviously, salmonella is one of the vegetative microbes, so you can kill it. This is how they use the iodine before surgery. Phenol and phenolic derivatives. Bless you. Phenol, I talked about it before, didn't we? Disrupt the wall and denature protein. Disrupt the membrane and denature protein, okay? It's bactericidal, fungicidal, virucidal, but does it kill the endospores? No. I mentioned 5 things that kill the endospores, and you need to remember all these 5. This is not one of them. Phenol is not used as antiseptic. It's questionable because of the high toxicity. Okay? Some of them can be added to the soap, like triclosan. This is an antibacterial that's added to not all the soaps. Sometimes they add it, which is one of the derivatives of the phenol. Chlorhexidine. This is a type of soap surfactant that denature proteins. It can be used for the skin degerming. Which one of those is not correct? I mean, which one of the 4 is not true? Does it kill by denaturing protein? Yes. Is it light sensitive?
Yes.
You're not supposed to leave the Clorox outside. This is light sensitive. Can we use the chlorine to disinfect water? It's used in a small amount. Slow the release of iodine? No, we didn't say anything like that. So it is D. How about alcohol? Alcohol, there are different types of alcohol. Ethyl alcohol and isopropyl alcohol. These can both be used for antimicrobial, and it's intermediate. 50% or higher, they dissolve the lipids and coagulate proteins. And this is important to remember. This is one of the cards that you're going to do. Okay? Are we clear here? Put chlorine on one side, how does it work? Alcohol on one side, how does it work? Phenolic, how does it work? Okay, so alcohol at the concentration of 50 or more, this is how it works. This is going to dissolve the lipids and the nature of the proteins. This is how it works if it is 50% or more. Hydrogen peroxide. If it is in a strong solution, it can kill the spores, but it's toxic. So because it's toxic, they usually use it for low concentration. If you increase the concentration, it will kill the spores, but it's toxic, specifically for the eye, or if you ingest it or something, it's very toxic. But if you use it on the surface, it's okay. Aldehydes, how do they kill? Alkylating proteins and DNA. Is that important? This is the most important. It should be on your cards. Okay? Just the way it kills. And examples. Glutaraldehyde, formaldehyde, these are aldehydes. And this is how they work. Alkylating proteins and DNA. Some gases can be used, an aerosol, like ethylene oxide, propylene oxide, chlorine dioxide. These are all gases and aerosols. And they used more for plastics. If you use it in higher concentration, it can be antimicrobial. How about detergents, like soap, for example? It mechanically removes the microbes, but it will also work as a surfactant. What surfactant means? Surfactant means decrease the surface tension and break down lipids. Surfactants. Do you remember the surfactant in the alveoli? Decrease the surface tension of the alveoli to keep it open. Something very similar, the soap, exactly. You know, if you think about it, like how did they make the soap or anything that's similar to that? To clean the dishes, how does it work? It's the same exact idea of bile. Did you ever think about it, how the bile works? Where do we make the bile? In the liver, and you store it in the gallbladder. And what's important about the bile? What is it important for? Emulsify fat. This is the exact idea of the soap. Okay? So the first time they thought about it, they say, okay, so the bile contain bile salts, and the bile salts emulsify the fat. You know what emulsify means? Like this. Look, this is a droplet of fat. Okay? If you want to work on this droplet, it's hard, it's big, right? You work on the surface only. So you break it down into smaller pieces. You can wipe it off, right? You can break it down. So this is how the detergents, generally speaking, how they work. And the denatured protein disrupt the membrane. This should be one of them. How does it work? I know this will be a lot, but I just need the name in one side. How does it work on the other side? But trust me, I'm doing that to help you study. You should do it anyway, even if this is not the activities. You should do it anyway, because this is extremely important. Each one of those. How does the detergent work? How does the soap work? Disrupt the membrane and denature proteins. This is how it goes. Okay? I don't know if I mentioned that or not. Hydrogen peroxide, how does it work? It produces oxygen radicals. I think I didn't mention that, but this is how it works. This should be one of your cards. Okay? You have a question? You can bring it next week. Yeah. While you're studying, you will not study anyway, right? Yeah. While you're studying, when you see something, write it down. And I just need to see it, but you keep it to yourself, because this is what you're going to study. And I would say this will make a big portion of the questions. Okay? How does the hydrogen peroxide work? It works by producing oxygen radicals. And these oxygen radicals are going to kill the microbes. So what's the answer for this question? What kills by producing oxygen radicals? Hydrogen peroxide. Heavy metals like mercury, silver, copper, they kill the vegetative cells in low concentration by inactivating proteins. Inactivating proteins. They don't use it that much, but if it is used, you need to remember this. This is one of your flashcards. Heavy metals like mercury, how does it work? Inactivating proteins. Dyes. Can you use dyes and antimicrobial like aniline dye? It can kill some bacteria and fungi. It can be used in antisepsis to act as antimicrobial agents, but it's not very effective though. Acids and alkalis, they have low level of antimicrobial activities. Organic acid, for example, they prevent spore germination and they slow down the growth of the bacteria and the fungus. Something like the vinegar. What's good about the vinegar, which is acetic acid? It inhibits the bacterial growth. Propionic acid kill the molds. Lactic acid prevent anaerobic bacterial growth. Benzoic acid inhibit the yeast. So these are different alkalis and acids that can be used. Organic acids, acetic acid, which is vinegar, lactic acid, and so on. This would be too much to memorize, so I would just say take a look at it. Okay? We already mentioned what you have to know. So these are just good examples, practical examples to look at it, but it's kind of too much to memorize. Just look at it, and what we covered before is the most important. And that is it.